Here I am Vadel Sagar. Welcome back to the our part number 2 of our present discussion regarding the chapter number 2. In the last section, in the last part, we seen a briefly introduction part of the present chapter and then some electrostatic potential regarding. Today also we go for the electrostatic potential in detail, and then after the second and third topic today we will discuss. Okay, so in the same diagram point of view, I am trying to explain you this what is electrostatic potential, that taste charge and the source charge, and that idea you may have clear from the part number 1 discussion. Consider any general static charge configuration means system of the charge that is you can able to see in this figure. We define potential energy of the taste charge q in terms of work done on charge q. We can define potential energy, that is u, in terms of work done, that we seen also in a yesterday's talk, or maybe I can say in a part number 1. Okay, now this work is obviously proportional to the q. How? Let me explain you. Because as we seen in a part number 1, the work done for the bringing the charge from the r point to the p point in the system, like that we need F external force for the drag the our charge from the r point to the p point. That is your force is the Coulomb force, and that force is F is equal to q1 q2 upon, or maybe it is expressed as the depending on the q. So the ultimately the work is also depends on charge. Okay, that is clear to you now. In electric field and force relationship, we very clear about the F is equal to QE. Then it is therefore which is convenient to divide the work done. Now trying to see here one more thing. Let me remove the what part I am next going. Before that I am trying to explain these things. Here electric field and electric force having the relationship with the Q. You can able to see what I am trying to say you. So is there any relationship of the electric static potential and work done, or the electric potential and then potential per unit area? Like that it is here I am trying to explain you. It is therefore convenient to divide the work, what work you have, which divide by the amount of charge. Because here suppose we have amount of work required to bringing from the r point to the p point is this much 5 joules suppose, then you have a 5 coulomb charge. Then what is the per coulomb charge work is needed? So is there any such kind of quantity in a physics which is independent to the q? I cannot 5 joule, but it depends on this 5 joule is depends on the total charge, because this charge if it is more, then more work will be required. If instead of this is the 5 coulomb, if this is not 5 coulomb, this is 10 coulomb, then the same distance travel for the same systems you need to do more work. So it depends on q. So is there any quantity? So the work done is the depensive. So is there any quantity which is independent to the coulomb or the independent to the charge? Yes, let me define this quantity which is electrostatic potential. So this is what the work done per unit taste charge. If we are divided with the charge, the characteristics of the electric field associated with the charge configuration, this leads the quantity which is electrostatic potential V. Okay, so this is what why in physics electrostatic potential terms comes into pictures in physics. This is what I am trying to explain you in this slide. Let's go for the relationship point of view. That earlier we seen that u, that I say trying to explain you, u is the amount of work. One more relationship, if you are come back with it, w is equal to difference of potential energy, up minus ur. Okay, that is your u is the amount of potential energy for the total coulomb. If you are, as I said you, this potential energy is 5 joule, then you have a 5 coulomb, then the 5 joule divided by the 5 coulomb, then you got 1 joule. So this is your 1 joule criteria. That 1 joule is independent to the your how much charge you have. 1 joule will tells you if you have every 1 coulomb charge, if you increase at the 1 joule, it needed to the work you need to do. Okay, this is what I am trying to explain you. U is the depends on Q. V is independent to the Q. How you bring this U? How you bring V, electrostatic potential, by dividing the electric potential energy divided by Q. Let me go ahead for that more explain reform form. So that we seen at the earlier in the part number 1. Work done by external force in bringing the charge unit positive from the R point to the P point, that W is equal to, that we see in W is equal to UP minus UR, subtractions of potential energy. But this UP minus UR divided by total charge, how much charge you are bringing, divide, then it becomes V, that it becomes V. This square, this bracket should be here in this side, the right of the equal. Okay, then it is clear to you if you are writing in your notebook. So this bracket should be right to the equal sign. Okay, so the work is nothing but the subtractions of electrostatic potential. It means difference of potential, because as I said you in part number 1, the potential is not much important than the potential difference. Potential difference is physically significant, that you may be able to understand or judge. Potential is, there is no much importance in physics. Work done by the external force in a bringing a, that is a one final definition of electrostatic potential. Electrostatic potential is what? It is nothing but the need to do work. It is a work done by an external force. You are applying the force, so you are doing the work on the system of charge, bringing the unit positive charge from infinite distance to the finite point. That is equal to electrostatic potential at that point. Is it okay? Yeah. Then we go for the 2.3 number point. So this is all about the what we have regarding the electrostatic potential, general definitions and all that. Okay, so electrostatic potential is nothing but the amount of work you need to do for the bringing the charge from the infinite distance to the finite point within the range. Now go for the potential due to the point charge, and that is very important point most time from the exam point of view, and then not only exam point of view, for the equations, examples and all that. Okay, so for that it is a very new or the similar kind of diagram we have. This again source charge from the another any charge we are bringing from the infinite distance. So as infinite, you can able to see that. So it is a, now you are bringing, trying to, okay, consider a point charge Q at origin. Consider it. Okay, done. We wish to determine a potential as our title. Potential we need to find at point P. So at from any point from the infinite to that point, which point? P point. So we are trying to find the potential at the point P, this point. Okay, please keep in your mind, this is the represented by the position vector r, which is a far from the distance to the q r from the origin. For that we must calculate work, because you know electrostatic potential is nothing but the amount of work. So ultimately we need to find how much work you need to do for the bringing the infinite distance to the finite distance at P. The amount of work, the work done against the repulsion force, because obviously that source charge is there. If it is source charge is positive, then your bringing charge is also positive, so the repulsive force are there. So whatever work you need to do which is against the repulsion force you need to do, that is your what the repulsion force on the test charge is also positive. Electrostatic force on unit charge is F is equal to Q upon 4 pi epsilon 0 r square. This is nothing but a simple Coulomb's law. Okay, because that one is unit charge, this is a Q and this one is also Q, so it is I am taking 1 capital Q and small q, but the small q is 1, so the q upon 4 pi epsilon 0 r prime square. Because here we are, why I am saying that it is a unit charge, because here is the electrostatic potential which is independent to the charge, which charge you are bringing, because it's a divided by already in a u. Okay, that's why it should be a unit, so that's why it's unit. And that is your magnitude scenario, this is your directions towards the r, this one r, obvious. Work done, this is a now what you find here at the end. Here the title says you need to find work. If you want to find work, W is equal to FD, but F you need first, so that's why we are go for the F. Okay, then we are going to work done against the force to bring a charge r prime to r prime minus delta r prime. What it is? Amount of work you need to do for the bringing the charge from the r prime, it is here, the charge is here, you need to bring from the r prime to here, this prime, this point. So this is the shifting is the delta r only. So how much is this much distance is r prime minus this part is r prime. This is not a quite difficult. Here you can able to see work done, what how much work you need to do from the r prime distance to the r prime minus r prime, delta r prime. It is here is there, and you are bringing near this much. How much this is, which is r prime total minus this part. Okay, so the we all know W is equal to FD. F as we seen this one, and D is displacement is delta R, only that part, this part. I am not going again and again this part. Okay, and r prime minus r prime is less than the r prime, so the delta r whatever you are coming which is nearer, so the always the delta r is final position minus initial position, but final position is comes nearer, so it is shorter than the final initial position, so obviously subtraction is going to be negative. So this is your what F, then W is equal to FD, so that F you are putting here, and D is nothing but the delta R, so this is your delta R prime, and this is obvious negative. So the work is amount of work you need to do for bringing the charge from this P prime point to the this point. Okay, this is delta Q, oh sorry, delta W is equal to force, this is a force part, up minus delta delta D, which is delta D is equal to minus delta R prime. This much displacement you are done. This is about the small work you need to do, but actually we have to bring from our charge from the infinite distance to the P point. This is our aim to bring. Now this is a small work, you know, then you can integrate over all the work you need to do. So you need to bring your charge from the infinite distance to the particular point R, which is a P point. So the W is integrating over the infinite to the R, Q 4 pi epsilon 0 R prime dr. Okay, so when it integrating, the delta going to be dr. Then this integrations of the Q 4 pi epsilon 0 is common out. Then the 1 upon integrations of 1 upon r square. Integration of 1 upon r square is a minus 1 upon r. Then minus and this minus is will be cancel out. So your final result is Q upon 4 pi epsilon 0 r prime, and you need to put the limit. That limit, if you are doing this in your calculator, sorry, in your page by this calculation point of view, so that Q upon 4 pi epsilon 0 outside square bracket 1 upon r minus 1 upon infinite. 1 upon infinite is 0, so only this Q upon 4 pi epsilon 0 r only left. Is the easiest step. As a 12th standard student, you should do this much. So now W is equal to Q upon 4 pi epsilon 0 r. This much work you need to do. This is defined now. What is our aim? You need to find the potential. Okay, as the definition we seen, the work done, how much work you need to do for bringing the positive side from the infinite distance to the infinite to the point is nothing but the electrical potential. So once you W you find, then V automatically that one. So this is now same to same we can bring for the V also. So the electrostatic potential VR is also Q upon 4 pi epsilon 0 R. So this is what we have our title, the electrostatic or the potential for the finite charge. Okay, and this is what we have, electric field E is equal to Q upon 4 pi epsilon 0 R square. Now see, all equations are same. Coulomb force F is equal to what? Q or the K Q Q or the Q1 Q2 upon R square. If you have electric field, then Q upon 4 pi epsilon 0 R square, or you can say K Q upon R square, Q only not present there. If here one more potential which is same in the scenario, K Q K. Why I am saying K? Because 1 upon 4 pi epsilon 0 is nothing but the K constant, K Q upon R. So there is only whole force is K Q1 Q2 upon R square. Electric field is K Q upon R square. Only Q is not there, one Q is not there. In the potential, one Q is also not there and one R is also not there. So the K Q upon R only. Okay. So now I am comparing the electric field which is KQ upon R square and potential which is KQ upon only R, not R square. So if I am drawing the way of reduction of the electric field and electric potential with respect to the R, it means distance. Obviously that is R is increased, this is a R axis. If your distance is increased, obviously the field filling, because the denominator is increased, the number of E and V will be reduces. So it is gradually reduces. When 1 upon R and 1 upon R square will be the same number, 1, if it is 1 meter, then the 1 square is also 1. So the electric field and electric potential will be same at the 1. So you can able to see there is a cut in a graph. Trying to see this E is reduce and it goes. So it is 1 upon R square. It means it is reduces more faster. How? Let me explain you. If you are from the system of charge to you are far from the 1 meter, okay, then you are finding your E is equal to KQ by R. R is your 1 meter. Now you are going to the double. It means you are at the 2 centimeter. Now 2 meter far from the system. Then you are finding the electric field, which is 1 upon 4 pi epsilon 0 1 upon R square, where your R is double. It means 1 meter to 2 meter. Now 2 square is there, so it will be the 4. It will reduces to 4. So electric field is always reduced fast than the electric potential. Why? Because it's a R square term in denominator, while in a potential we have only KQ upon R. It will not diminish as faster than the electric potential because it's the only 1 upon R. So if suppose again I am taking the same example, you are at the 1 meter and you are finding the electric potential, something will come. Now you are at the 2 meter, so 1 upon only 2, there is no square, so divide by the half. So it will be gradually, it will reduces slowly compared to the, you can see the graph is above bluish line for the electric potential. So ultimately we can take an idea from this graph is the electric potential will reduces more slower than the, it means not much faster, it will not much faster, not reduce than the electric field. So electric field is one another way, electric field is reduce or diminish faster than the electric potential. Okay, this shows that the electrostatic potential is reduced by the 1 upon R way, and electrostatic field is reduces 1 upon R square way with the values of R. This is one short example. Calculate the potential at the point P with this charge is this given, and now 9 centimeter is equal to the distance is given. So as we know, the V is equal to 4 pi epsilon 0 Q upon R. All numbers are given. Just you have to do calculation in your calculator. Second, B, hence obtain the work done in a bringing charge. So the charge is given from the infinite point to the P point. So the work we have to find does the answer depends on the path along which the again brought. W is equal to QV, as I said you. The Q is this 2 into 10 to the power minus 9. V is 4 into 10 to the power 4. So the work you need to do 8 into 10 to the power minus 5 joule. So work is always in terms of joule, and electric potential in always terms of volt. No, so that answer is the no, it's not depends on path. Work done will be the path independency. Any arbitrary infinitesimal path can be resolved into any perpendicular to displacements, one along the r and another along the perpendicular to the r. The work done is corresponding to the later will be the 0. So that you may not go in the detail, but I can say in a very brief way the potential or the work you need to do which is independent to the path. Thank you very much.